Next, we have Iran University of Science and Technology. So if the team of Iran can introduce their members.
Hi, I'm Farnaz. Can you hear me?
Yes.
I'm from Iran University of Science and Technology. I'm so glad that we are in this meeting right now. I'm here as the captain of my team, which includes Negar, Mahdi, Hossein, and Ali, and also guided by our dear professor, Dr. Mohsen Saidi, who helped us to finalize this project. As mentioned before, today we are here to present our solution to a real environmental issue that was raised by SWANA, and it's about evaluating the land jam limitations and also introducing and determining a new and alternative method for landfill emission estimates, especially methane. Thank you. If there's any question after the presentation, we are ready for it.
Thank you, Farnaz.
Thank you.
Stella, we are ready when you're ready.
Yeah, sure, we are ready.
Okay, so share the video, the recording.
Yes, correct.
Hi, this is me, Negar from Iran University of Science and Technology. I'm here from behalf of my team to present today. In this presentation, we first talk about the land jam evaluation and its limitations. Then we define two scenarios for modifying the parameters of a land jam formula by considering the weather conditions to report the methane emission estimates more accurately. Over the past decade, municipal solid waste has become one of the most significant environmental issues worldwide. Landfilling is traditionally a main biodegradable waste disposal method in many countries due to the ability for mass manipulations and simple management. Solid waste management is an interdisciplinary issue that affects various areas of sustainable development, such as ecology, economy, and society. Landfills are one of the largest sources of the methane. Landfill gas production involves four phases. The first phase is aerobic and the primary gas produced is CO2. The second phase is characterized by a decrease in the O2, resulting in an anaerobic condition where large quantities of CO2 and hydrogen are generated. In the third phase, the production of CH4 starts by reducing the CO2 produced. CH4, CO2, and N2 become relatively constant in the end phase. Due to anaerobic decomposition of the waste landfills, methane is produced and constitutes about 50% of a landfill gas or LFG. The LFG is produced from a series of a chemical and biological reactions that typically occur in a mass of disposed waste through the landfills. An LFG is generally composed of a methane, carbon dioxide, nitrogen, water vapor, and other innumerable traces. The amount of methane that can be generated from a landfill depends on the composition of waste, moisture content, age and depth of the landfill, ambient temperature, and precipitation. Over the years, a large number of numerical and mathematical models have been developed to estimate LFG based on a zero, first, and second-order approaches. However, second-order models are not commonly used because of the required parameters in each model are often so uncertain that they negatively affect the accuracy of the model outcomes. Likewise, zero-order models do not reflect the biological LFG generation process. Because of these limitations, simplified approaches have been developed based on a first-order waste decay or FOD. Among these FOD models, LandGem, AlphaZorb, IPCC, Skull Canyon, and EPER are widely studied and reported. Models for estimating landfills gas production are useful tools for projecting these emissions over time. Various models are available to predict the LFG emission. Most projects apply first-order decay models. All these models have their limitations and strengths. LandGEM of US EPA is the most efficient model. LandGEM is primarily developed by US EPA's researchers to bring most of the large US landfills into the Air Quality Regulatory Program and to extend them for regional emission inventories, which are governed by two main factors. The methane potential, or L0, which depends on the type of base composition, and the constant generation of CH4 or K, which varies according to humidity, temperature, precipitation, pH, type of base, and nutrient disposition of an anaerobic process. LandGEM has many advantages, including ease of use, low cost, and fast computational results. On the other hand, there are limitations such as the model doesn't consider the different composition of the waste disposed in a landfill, indicating that the waste composition directly interferes with the gases generation from the composition. Another one is the LandGEM assumes a 1-year delay in a methane generation and 0 decay during this period. These issues make the difference between the calculated methane by LandGEM more significant than the actual value. The model doesn't consider the type of base cover, while research has shown that the class of cover and the soil can be effective in the methane emission. To evaluate LandGEM, we selected 39 landfills in the various US states. The chosen states had a different climatic characteristics with a minimum and a maximum average annual precipitation for these 39 landfills being 9.7 and about 54 inches respectively. All the selected landfills had the same features, such as all were in operation and open, and all were equipped with the gas collection system. We also selected landfills that do not have leachate circulation. The observation value of the methane generation is based on two formulas that's shown below. The explanations of these two formulas are given in the reference, but for a brief explanation, the first equation is derived from the gas collection system. Then, since some gases are immersible, the amount of gas collected is always less than the amount of generated. Therefore, the quantity of the methane reported is always the minimum quantity that was generated in a landfill. We selected landfills which is value the first equation is greater than the second equation. The landfill gas emission model, or LandGEM, is an automated estimated tool with a Microsoft Excel interface that can be used to estimate emission rates for methane from these 39 municipal solid waste landfills. First, we run LandGEM with the default values. For any landfills with a precipitation greater than 25 inches per year, L0 and K were equal to default values 100 and 400s. And for landfills with less than 25 inches per year, the default values were 100 and 200s. To evaluate the LandGEM, we compared the result obtained for the methane values generated by the model for 2010 to 2020 with the observed value recorded from the GHG website. In a 36 landfills reviewed and 200 data, model results were lower than the observed and underestimated. And also, according to the chart, precipitation is increasing slightly, and the K value is expected to increase just as slightly, but in most places where the temperature rises suddenly, the K value also rises abruptly. Then we found that the K value depends on the temperature and precipitation, and we have to also consider temperature to determine the K value in a better estimations. This difference led us to introduce new values for L0 and K to minimize error. To continue the study, we defined two scenarios. First, modify K and modify L0, and the second was modify K and default L0. In the first scenario, initially, we need to obtain the value of L0 according to the base characteristics using the following equation. After acquiring the value of L0, we use inverse modeling, in which we obtain the value of K by placing the known parameters in a LandGEM equation, which was coded by a MATLAB software. After obtaining modified values of K, we use regression analysis to extract new equation for K based on precipitation and temperature. To increase the accuracy of our work, for the average annual precipitation, we define 3 periods, less than equal to 20, 20 to 40, and more than equal to 40 inches. We determine the equation for each of these periods. These diagrams compare the sum of normalized error for Langem and Scenario 1 in a CAA and inventory modes. Less error rates shows better results. In some landfills like a CA1, ND, TX3, the error rates are significant in a Langem model for both CAA and inventory. These diagrams shows that the both scenarios have a better result than the Langem. In a second scenario, we assume that the value of L0 was 100 and then obtain the value of K by inverse modeling in a MATLAB by using the amount of the methane observed. In this scenario, as in the first scenario, we use regression analysis to extract 3 equations for K. As shown in the equations, for both scenarios, we consider the effect of temperature and precipitation on K. In the next step, we define the sum of normalized error value to evaluate the methane generated using these scenarios. The normalized error diagram in scenario 2 shows that, as in scenario 1, the error rate is less than the Langem model. In this scenario, more landfills have fewer errors. In other words, this scenario has a better result than the first scenario and the Langem model. Our results show that, comparing the methane generated using the equations in the first scenario with the methane calculated from the Langem default values in a CAA and inventory modes reduced the error rates by approximately 21 and 30% respectively, while our second scenario was able to perform about 34% better than Langem in inventory mode. Thus, the result from the both scenarios indicate that using these scenarios may show results closer to the actual values. As you can see in the map, we use 8 out-of-scope landfill sites for validation of equations. The review of sum of normalized error for inventory and CAA for scenario 1 shows the error rate reduced by approximately 32 and 22% for inventory and CAA compared to the Langem. But the result of scenario 2 validation were better and could reduce the error rate by about 35%. Investigation of the 2 scenarios show that both significantly reduce the error rates and report better values than the Langem. The sum of normalized error in the first scenario in inventory mode was 90.5, lower than we expected than the sum of normalized error in the second scenario in the inventory mode, which was 20.4. But when we compare the error for each scenario with the Langem, contrary to our expectation, the percentage of a reduction in a scenario 2 in inventory mode was about 5% higher than the scenario 1 in the inventory mode. This could be because of the announced composition were inaccurate because of our calculations error. Climate change and global warming annually increase the temperature, and rising temperature increase the methane generated in the landfills. This is important for estimating the amount of the methane generated in the future. Since Langem calculates the methane generated less than the observed value, this can affect the design of gas collection systems. Therefore, it's suggested that in the Excel sheet of a Langem software, the amount of precipitation and temperature can be questioned by a user so that the more accurate value can be estimated. By scanning the QR code below, you can access our suggested Excel sheet, and by adding temperature and precipitation, you can obtain the K value for each scenario. At the end, we wish to acknowledge the help provided by the technical and support staff of the Iran University of Science and Technology. We would also like to show our deep appreciation to our supervisor, Dr. Saidi, who helped us finalize our project. We also thank SWANA for the opportunity to participate in this competition. A special thanks to Alex and Ludovic to answering our questions. Thank you for your attention. We are ready to hear your questions and comments.
Thank you, Farnaz.
Thank you so much. We are ready.
Okay. Let me just start out by saying I think this whole assignment was especially challenging because, frankly, the landfill gas industry doesn't have a solid answer to this issue. There is no, after doing this for decades, we have to approach it with some degree of humility. So, if I haven't been able to figure it out completely after 26 years of research, I don't expect everybody to figure it all out, particularly given the level of research. One of the issues that I think that you find in the research, which is somewhat misleading, is that temperature is an important factor in landfill gas generation. Well, it is inside the landfill. Ambient temperature is not necessarily an important factor, and usually it's not, because landfills themselves inside, they generate their own internal temperatures, so they're relatively independent. But I understand, I think all 5 teams were somewhat tripped up by this issue, and I think it's unfortunate that the IPCC model splits out temperature. So that aside, I think the questions I have to do with well, first of all, I think you guys did an excellent job at addressing the assignment, which was to evaluate LandGem and your alternative model with data. And I think the other confusing thing about this area of work is that it's not always 100% clear what is measured data and what are estimates. And in the greenhouse gas reports, there are quite a lot of estimates that sometimes might appear to be data. And so I guess my question is, you spelled out your greenhouse gas equations that you were using to as data to compare to the model. And I think maybe you could explain how that works. How do you get from measured methane flows via a collection efficiency to a generation number that's compared to the model estimates?
As a first step of our work, when we were going to find the methane generation in GHG website, there were 2 kind of values. First was written methane generation by 7 equations, and the second was by 5 equations. We didn't know the difference, so we went and surfed the net, and we found that a document that was referenced below the page, and we found that the equation 7 was based on gas collection. And as we know, the emitted and the generation is always more than the collection one. So the equation 7 just calculates the minimum, the minimum value of the methane generation. And because of that, we use this value, the value that was set by equation 7, and in sites and landfill, that equation 7 was greater than equation 5. But equation 5 was based on a modeled methane that some kind of parameters of waste composition was considered in that. So we tried to use the landfills and the sites in which equation 7 was greater than equation 5. That was our generation method, which was compared which was compared with model 1.
Okay, yeah, just to explain, they're both estimates.
Yeah.
They're both estimates. One is based on a model, and so basically it's measured flow divided by a model estimate. So it's, so if we question the model estimate, we certainly can question that collection efficiency. The other one, the one that you used, is based on cover type. So it assumes that you have, I think it's 60% in daily areas with daily cover, 75 intermediate, and 90 or 95% in areas with final cover. What it does not account for is how efficient your collection system is operating. So just to be aware that those are estimates. So when you compare models to estimates, we should also take into account the possibility that those collection efficiency estimates might be in error.
Sure.
My other thing was when you calculated your L0 values, I guess it seems like you did a blended LO that was a weighted average of IPCC values for different material types. Is that how you ran the calculation of your L0 value?
Yeah, there was a formula which was set by IPCC that was in the PowerPoint, and we used the data from GHG website about the waste composition, different types and different percentages. We used them in that formula and obtained L0 based on waste composition for each landfill.
Okay. So towards the end of your presentation, you have graphs, charting model error. Maybe could you walk us through again how do you define error, and recognizing that we have estimates. So you're comparing model estimates of generation to the greenhouse gas estimates of generation using that equation 7. Is that right?
Yeah, by using normalized error, actually sum of normalized error with, comparing one time the observed with our estimations and observed with the land gem, use of sum of normalized error, we obtain those reduction in error. Comparing our model with the land gem.
Okay. I think I've gone through my questions. I don't know if anybody's got anything more.
I'll just say cool use of the QR codes on there. That was pretty good presentation.
Thank you. Thank you.
My questions were going to be much similar to what Alex had related to, don't forget that none of this is known. So when you're comparing the model result to a known value, there is no known value except for the gas collection rate. But to get to the collection rate back to the generation rate, you have to make an assumption of what the collection efficiency is. As long as that's understood, I think that's a key outcome of this exercise.
Yeah, I think we're here. A lot of what we're doing here is to try to help you guys transition from academic world to the professional world. And there's a lot of situations where academic understanding can only take you so far. And the trouble is here, the landfills are like these sort of black box animal that doesn't really behave according to theory very consistently. So, theory can only take you so far. And then we find oftentimes that when you measure real values, they're not easily explained.
Yeah, sure. Thank you.
One statement would be also great job is the collection efficiency plays a big part of landfill gas. What drives the collection other than regulation, there's a lot of small landfills that they're not mandated to have a collection system, is the value of gas to energy, which is a huge project that involves millions of dollars. So if you're overestimating what you anticipate collecting, then that's a a big disadvantage, and it'll cost the client a lot. So one of the biggest thing we use when we develop models, site-specific behavior, if there's bottom liner, there's no bottom liner, it all is integrated in the collection efficiency. So, sorry. But, so, I mean, that's just a statement for you guys. When you transition, you'll see that cost is a big issue, and return on investment is another, you know, it's an economic issue. So, and what we've seen, and Alex has seen, we've seen landfills that they estimated the collection as twice what they actually are receiving. After you account for everything, you find out that they're there where they're supposed to be. It's just when initially it was estimated double the volume. So they designed and paid for capital investment double, and realized that no, you know, if you really tweak the collection efficiency, then you get closer to a better number, basically. But other than that, I'm good.
Thank you. Thank you.